Everyone. For those of you who stayed through all 4 sessions, I think it's well worth it. It's impossible to discuss the subject matter in 15 minutes. It's a world of information. My name is Frank. I'm pleased to introduce Sifan, if I mispronounce your name, Kahale. Sifan wrote a bio, but, it's Sifan. Sifan is the guy who makes this, or the lady who makes this work. He, or she rather, always records every presentation. And it's also streamed live. So in addition to the activities related to pan-stars, which you're going to get to be more familiar with, she makes IFA what it is in terms of having documentation and recorded documentation of all the presentations. If you're ready, don't come to the monthly meetings, please do. Out at the front desk, you can sign up to get an email when they're occurring. They're all fascinating, every single one. I never miss a meeting in the evening. And Sifan makes it possible to see it on the internet after the fact if you don't see it live. So you can come here, you can see it streaming, or you can see it after the fact. Please welcome Sifan. Thank you very much. What did I miss? Oh, I didn't give you the... I don't turn it over.
Let's see if I can. Had to find something I had a belt. Okay. Hello, everybody. How's everybody tonight? Wow, the last talk and you're still here. That's pretty good. Well, thank you for being here. What I'm going to do tonight is talk a little bit about not just pan-stars, but also Faulkes and maybe a couple of the other observatories that are up there. And I thought it would be a good thing to show you just a little bit about what it takes to operate an observatory. You know, and I'll show you a couple different ones, basically pan-stars, and then also the Falx Observatory that's up top. And we'll go through and take a look at that. Now, what I have here are virtual models. These are three-dimensional models that are built in a virtual world. And this is very much like Second Life, where you have an avatar and you walk around and you do things. And in fact, in the back, that's the other thing that's happening right now, is there's a number of people in Second Life that are sitting with their avatars down here in these seats, watching what is being telecast on this middle screen here. So right now, they're watching in Second Life. This is a standalone grid, and that way I can control it a little bit better and everything else. So this is offline. Nobody else can go into this particular grid. You know, and that way I can do the things that I need to do without interference or anything else. So, but everybody else is watching us right now on this particular screen, which probably, well, yeah. So first thing I'll do, and this is what I was sort of showing upstairs too. So if you had this first part of the presentation, I'm sorry. This will be sort of a bit of a repeat. So this is pan-stars 1 on the right, and that's been in operation for about 6 years or so, taking science for about 5 years. Pan-stars 2 is the one that's over here on the left, and that is just finished building last year. But like any observatory, once it's finished building, it takes about a year or 2 or 3 as it goes through commissioning. Part of what we need to do is to understand all of the drives and everything else and the mirrors and everything else that's in there, and we have to write the equations necessary to very, very accurately control these. So when we tell it to point at a star, it's like going to really point there you know, with high degree of accuracy and track it. And that takes about a year and a half or so to put together. With pan-stars 2, we are getting very close. In fact, we do a lot of engineering work on it right now, but we also do some science work. It's already found a comet. It's already found a number of NEOs, near-Earth objects, and it's already found a PHO, a potentially hazardous object. That's one that's going to be sort of close to us that we want to know a lot more about. So even though it's still in commissioning mode, it's found some things already for us, and some things that some notable things that we have to be careful with. So what I'm going to do is just sort of go through and show you the major parts of the telescope and what we need to do when we turn this thing on at night. So actually the first thing that happens, and that happens in the morning, is we initialize the telescope. We put it in what we affectionately call its happy place. Yes, telescopes have happy places. And this puts it there, and that's nice because then it's all set and ready to go later on at night. If it's not in this happy place, we usually have work to do to get it back in happy. So now it comes nighttime and we want to open this up. So this is about 2 hours ago they actually did this. So this is a real model. It's to scale, etc., etc. So it's just like the real one up on top of the mountain. And if you went up to the mountain and took a look at this, this is what you're going to see. Now, the benefit of modeling this in the virtual world like this is that I can show you angles that you wouldn't be able to see unless you were inside of a helicopter. So this is nice because it gives you a much better idea of what the telescope is and what its parts are. So inside of here, of course, is the telescope itself, and there's a lot of metal inside of that. So the second we open up these, the dome shutters and everything else, the inside temperature is going to be a little bit different from the outside temperature, and as a result, if it's cooler or warmer, the metal's going to shrink or expand, and our mirrors and everything go kaput, and there we go, we can't take a good image. So we have to wait for all that to settle out. So the faster we can have that settle out, the better we are. So one of the things we do is we have 4 of these big doors, and I have to open those first. But before I can do that, I need to take a lock. And that's because this can be operated from anywhere in the world, if you know where to go and if you know the proper passwords and things like that. And I've actually had to do this from different places when they had a problem. I'd have to come in. I've been in China, I've been in different places where I'd have to come in and actually, get into it and take the lock. So now that I have a lock, nobody else can mess with me. Nobody else can start turning things and, sitting there, why did that happen? So now I've got complete control of the dome. So the first thing we're going to do is open up the vents. And you'll see these things slide open. And that opens up, it's a huge area, and that lets a lot of air into the dome itself. The next thing we'll do, of course, is open the dome slit themselves. Okay, exposing it. Now I've got a lot of air coming through there. It's still going to take a while for it to equilibrate with the outside temperature. And as you can see, there's a lot of metal in the structure, of this telescope. So all that metal has to come to the same temperature as the outside before we can take any images at all. And I'll show you why in a little bit. Meanwhile, earlier this morning, we found out that when we closed down the telescope, if you take a look at what the temperature is then, that's pretty close to what the temperature is going to be at sunset. So we found that we can turn our air conditioners to that temperature, and the inside temperature will be close enough to the outside, so it'll be a little bit better. But now that I'm open, I don't need that, and if I have that on, it's going to be throwing air across, my telescope, and again, making the image not all that great. So we want to turn those off. Okay. Then the next thing we want to do, in fact, something we probably should have done long before we opened this up, is we have the lights on. Oh, dear me. So let's turn those lights off. Otherwise, the other observatories at the summit are going to be yelling at us. We don't want that. So now, the next thing I'm going to do is turn something on called the hurricane fans. And I'll tell you why in a minute. But what these are going to do is they're going to suck the air down from the top, down through the observatory stack itself, and then through these double doors that you see over here, and then out here. Now, normally there's a garage door that's shut right here, but I left that open just so we could see what's happening inside. So I'm going to turn on the hurricane fans, and you'll see that these shutters open and these shutters open, and those fans go a lot faster than this, and if you were standing out here, you would know why we call it the hurricane fans. Okay, so at this point, we're almost ready to take images. one more thing that we have to do, and that is that we have these covers over our mirror. Because again, the mirror is the most expensive part of everything up there. And as we open those dome shutters, wind and other things could have thrown dust and tiny rocks and pebbles up there. So we want to have this closed and protected, until not only do we have this completely opened up, but we establish the correct airflow and everything else, and everything is stabilizing. Once everything is stabilized, then we'll go ahead and open up the mirror covers. And that exposes our main mirror. Now, this particular type of telescope is called a Ritchey-Chrétien. And what happens is the starlight comes down from the top, hits the mirror on the bottom, and the mirror is concave, right? So it's going to reflect it back in a cone up to the top again. And up on the top, right in here, is another mirror. So the light comes down, gets reflected back up into a cone to this mirror, and then from that mirror it gets reflected back down to a hole in the primary. And if we take a look at the primary mirror, we have this tube, and that's the hole that goes right through to our instrument stack underneath. Now, for pan-stars, this is the world's largest digital camera, 1.4 gigapixels. A gigapixel is 1,000 megapixels, so it's very huge. And all CCDs are black and white, or gray, okay? So in your camera, for example, they cheat. And they take each a set of 3 pixels, and they paint one red, one green, one blue, right? So you read that in, you put it together, and you get color. So if you have a 9 megapixel camera, you have a 3 megapixel picture. We don't want to waste any pixels. So instead of painting pixels, what we do is we throw in a filter. So we have 6 filters that we can put in, and each of these filters are, I think, like close to $1.5 million. So these are extremely accurate filters. And we're not interested in just red, green, and blue. There's 6 different filters that we have. What these filters are actually doing, what any filter actually does, is it breaks the light apart. You've got the spectrum for visible light, right? We also go into infrared and ultraviolet. And these filters take out a section of that. Okay, so we have 6 filters across the section of light. What that does is tells us a lot about whatever we're looking at, what it's made out of. So if we look at these 6 different filters, the same object in these 6 different filters, we get a lot more information about what that is, and and also how fast it's traveling. A lot of other information can come out of that, and so that's why we use this filter. So I'm going to put in a red filter, and again, this is just a simulation. And the one that's above here, that's the shutter. So that's what actually opens and closes when we take our picture itself. So with that, then we're all set to go ahead and take a picture. So we'll do that. Now, this type of telescope is an alt-az telescope. There's 5 stories that's inside of that. And so when I want to take an image, let's say there's a star that's over there, I have to turn the entire building to look over there, and then I raise or lower the telescope to look at that particular star. So that's what I'm going to do right now. We're going to slew it, and we'll aim it so it's this way. So that's going to be about 270 degrees, and I'll drop the telescope to about 50 degrees, and we have something that's a rotator. I'm going to put that at minus 90. And then now the real telescope doesn't move that fast. Sometimes we wish it did, but it doesn't. But that's about 270 degrees. This is 0 over here, so across that's 270. And yeah, that looks like about 50 degrees. Okay, so now what we can do is take a picture. And we'll just take a 5. Now, in this case, I have a little laser light that turns on. We don't have a laser up there. This is just in the virtual worlds to show you that it's really taking a picture, and it's also showing where it's pointing at. So if I took another one, let's a little longer here, 30 seconds. If I can find that, this might be a little bright, but. I can't really see it with this screen, but this is going to be pointing up, and you actually see where it hits the dome up here. So you can actually see where it's looking at, the actual star dome. Now this star dome that's in there is turning at the same rate that the stars above us. So you should be able to go, not this one because I haven't stopped, but in Second Life, the one that's in there is turning exactly as we are outside. So if you were to look at this, go outside and look up, it's going to be the same. Which means that the telescope, when it aims and takes a picture like this, you can look up to see what it's actually looking at, you know, where it is in the sky. So now that's the pan stars. And I've got one other one over here, and this is the Falx Observatory. And the Falx is the one that has the clamshell dome. And it's pretty cool to see, okay, when you're up there. And this one used to have a web page that allowed me to get in to find out exactly where it was pointing at this moment, and also the picture, the last picture that it took. And I had this program to monitor and watch and follow exactly what Falx was doing. So for a while there, you could come in here, or in Second Life, and you could actually see where Falx was pointing, again, up to the sky, and see the real sky that's above, and then take a look at the pictures that I was taking. Let me just show you the bottom of this one is a little bit different. I mean, it still has mirror covers and everything else, but the bottom of this, instead of pan-stars, which is a survey instrument, all we're doing is we have this 1.4 gigapixel camera, and we're going through and taking, you know, pictures of the sky over and over and over again, trying to find NEOs and asteroids that are up there. The Falx is a research instrument. So as a result, they want to put on different types of cameras or different types of instruments so that, you know, for whatever their research is doing. So they actually have this octagonal unit at the bottom of theirs. It actually has a mirror inside. So you can mount all these different instruments on it. You can see here's a couple, here's a representation of a few different instruments. 9 in total, because you have a straight through as well. Okay, and then you can command this to flip to whichever, there's a mirror inside there, and you can command this mirror to flip to whichever instrument that you want to use. You know, and then each instrument has different parameters too, like for instance, which filters do you want to use? And so you can program all of this in, they use a Q as well, and take pictures. There's a spectroscope which will break out the different colors and frequencies of what you're looking at. There's some specialized infrared cameras. There's a general purpose camera down here that'll take red, green, blue, etc. So this was a very useful instrument, still is. I mean, it's up there. It was at one point for the exclusive use of the kids. And the kids that would use this in school are in England. So during their daylight hours in class, they would use this telescope, which was dark, so they had access to a live observatory during their school day. Same thing here. The kids in Hawaii have access to other telescopes that are in Africa and other places around the world, so that they can use a telescope during the day, but it's night over there. Okay. Now, since then, they've changed this over to be a more of a research instrument, and so and that's why, for instance, I can't get at you know, the parameters to be able to set this to follow it anymore. But that was pretty cool when it did. So I think I've probably seen you back there going, yeah. So it's out of time. But thank you very much. Thank you very much. Thank you for staying. Yes. That's actually part of the commissioning phase, about a year and a half. It's not so much the metal and things settling in as much as it is getting to understand. When you tell the motor to do this, what does it really do? You know, and then programming in the corrections for that. For instance, underneath these mirrors are actuators. In some cases, 32 different actuators, where we can actually tilt the mirror, you know, in different ways, lift it, drop it, bend it a little bit. There's all kinds of things we can do with this mirror to get it into focus. And you can imagine trying to figure that out. You know, and in this, because when you tilt the telescope, you know, this you know, half-ton mirror is coming up, and this glass is now going to be pressurized and bent in a certain way. You've got to unbend this or bend the other part over to, to make it match. And then you point the other direction, there's something else going on. And, so you have all of this that has to be figured out. For this particular angle, what do I have to do? And then, not only do you have that, you have the secondary mirror on the top. It's got a hexapod, and I can raise and drop that. I can tilt it in any of the different directions. I can also bend it. So now you get two of these complex instruments that you have to figure out the equations for. On pan-stars, the equation is 26 terms long. That's, cosine of this plus sine of this plus that. 26 of those terms long. And I still had one quick little story. Okay, yeah. One quick story as an example. Something was wrong during the commissioning of PS1. This is about 5 years ago. And the two principals, one is in charge of the camera, one's in charge of the telescope dynamics and things. And they were having this heated argument. I mean heated. I mean, they were at each other's throat about this. And they were discussing this 26-term formula. And they were vehemently arguing about it. And all of a sudden, one of them stops, goes silent. And the other guy stops and goes silent too. Says, I know it's wrong. Term number 23, that's supposed to be a minus. He was right. And from that point on, everything worked. And the site manager and myself were up there with him. So the four of us. Bob looks over at me and says, I could have told him that. But can you imagine that? To be able to have that formula, not only the formula in their head, to be able to vehemently argue about it, right? But to be able to understand what each and every one of those terms is, and then to be able to pick out something as simple as that. So it's my hat's off to some of those people. But that's what's going on with the year and a half, is figuring these kinds of things out. And it is in no way simple. It's a huge, huge effort. But yeah, that's settling, that's the metal, that's the performance, that's the bending, that's the temperatures, that's the everything. Yeah, all of that gets thrown into these equations. There's temperature sensors on all of these kinds of things. So, it will go and adjust things and turn mirrors and everything when it finds that, say, the left strut is a hair's width larger. Yeah, you'll actually hear the mirror actuators going as it readjusts in real time. So it's amazing, and it's complex, and it's pretty cool. It's a lot of fun to see what they did and what goes into these things. So it's very, very accurate.
Tom Shad told us that DKIST is going to take 500,000 pictures of the sun every day. How many pictures does Pan-STARRS 1 take every night?
Okay, about 600. See, but you have to remember, DKIST is looking at a nice bright star, right, the sun. We're looking for things that are extremely dim. In fact, if you haven't seen I've got a little black asteroid. It's a mock-up of an asteroid that Hayden with the 3D printers made, and it's on the table in the back there. If you go and take a look at that and see how black that is, that's about as black as this. That's the color of these things. So the tiny little bit of sunlight that these things are reflecting, that's what we're trying to pick up. So so as a result, in order to do that, you have to have a large telescope, you have to have a very large camera like we have, and you have to leave it on for 30 seconds to 60 seconds at a time, to grab that. And then not only that, you take multiple pictures of that same spot, and you collapse or add those together, and that gets rid of, a lot of the noise and everything else, and makes the image much, much sharper. So those are 600 pictures, when individual, not images that we take, but composite images by the time we're all done with all of the rest of this that goes on. And when I talk about complexity of this up here, that's nothing. The complexity of actually finding this out of the data, finding these things out of the data, there is 32 racks. This is a computer rack, you know, about like this. Each rack holds 10 to 20 computers, depending on the size. Each computer has about 16 cores in it, and they're going at probably close to 3 gigahertz. So it's extremely fast. You multiply all that out, and that's one heck of a lot of compute power. That's what it takes to be able to crunch this data, do the comparisons, and then come out and find something that's moving. You know, so that's even probably more complex than what's going on upstairs at the telescope itself. That's down in Kihei at the High Performance Computing Center.
Is that technical center?
Pardon?
Is that technical center?
Yes. Yeah, on Lapoa, you know, at the end of Lapoa Street, yeah. I don't have my badge, but yeah, you have to wear a badge to get in there. And goes
Sifan will stand by if you have a
oh, yes, definitely. Thank you very much.